Well,
good day, everyone, and welcome to another interesting session of this year-long series, which the IEEE Electron Device Society Delhi chapter is jointly organizing with the Upadhyaya College, University of Delhi, under the aegis of the Department of Biotechnology Star College program. And this program is also being supported with the National Academy of Sciences India Delhi chapter. And today we have with us Professor Charles, who's from Department of Electrical Engineering, National Chung University, Taiwan. And he'll be talking to us on the topic bandgap engineering and device applications of dilute nitrides. He's a well-known figure in Electron Device Society and is also the Yushan Fellow and Research Professor in the Department of Electrical Engineering, National Chung University in Taiwan. And he's also a distinguished professor emeritus in the Department of Electrical and Computer Engineering at University of California. He was in the UCSD faculty from 1988 to 2018 and was the EC department chair from 1999 to 2003 and was an associate dean of the Jacobs School of Engineering from 2004 to 13. His research interests include novel compound semiconductor heterostructures and nanostructures for electronic, optoelectronic, and photovoltaic applications. He was a distinguished member of the technical staff at AT&T Bell Labs, New Jersey from 1980 to 1988, and he earned his PhD in engineering and applied science from Yale and his BSc honors in physics from the McGill University in Montreal. He's a fellow of the IEEE, American Physical Society, and the AVS Science and Technology Society. He received the Taiwan's Pan Wen Yuan Foundation Outstanding Research Award in 2009, North American MBE Innovator Award in 2011, an honorary doctorate from Linköping University, Sweden in 2013, and the IEEE Region 6 Western US Educator of the Year Award in 2014. With these words, I now invite Professor Charles to kindly share his screen to deliver his talk.
yeah, okay. Okay, first I want to thank Tina for give this talk. And so as mentioned, the title of my talk is Bandgap Engineering and Device Applications in Dilute Nitride. Right now, I'm in National Tongxing University in Taiwan, but all the work I'll be talking about actually were done at UC San Diego. And right now in Taiwan, I'm working on a slightly different project. Okay. So on the first slide, I also acknowledge my former students who contributed to this work. And that's they are on the first bullet point. And then my collaborators at University of Linköping and UC San Diego, as well as Berkeley, and National Renewable Energy Laboratory, Northwestern University. And then the last bullet is funding agency. So here's an outline of my talk. I'll be saying a few words about molecular beam epitaxy, or MBE, and specifically focusing on electron diffraction. And then I'll be talking about this dilute about to a couple of sensors. And as a result, there are three bandgap engineering parameters that are affected. MB, bandgap bowing, band alignment, band structure. And so these three bandgap engineering parameters are different devices which have improvement from this incorporation of dilute nitride. And then I'll talk about future prospects. So molecular beam epitaxy is a highly versatile thin film growth technique It's growing layer by layer, and it's done in an ultra high vacuum condition. You know, atmosphere is 760 torr. Ultra high vacuum, we are talking about 10 to the minus 9 torr. And here we liken NBE to be spray painting with atoms, meaning that in the growth chamber, we have diffusion cells with materials like gallium, arsenic, aluminum, indium, and so on. And we heat them up to high temperature so that we have atoms diffusing out. But to stop them from coming out, we put a shutter in front. And so when we want to grow material, AB, we open the shutters of AB. And ABC, we open the shutters of ABC. And then again, we close the shutter for C. So we can grow such a super lattice structure. And because the growth rate is about one atomic layer per second, and then the shutter closing and opening is about 0.1 second. So we can grow a very abrupt interface. And for dilute nitride, we use a RF plasma nitrogen source because N2 is very stable. So we need to create a plasma to produce excited species. Yeah. And so here, I also, you may see that, you know, why we wrap a $1 million machine with aluminum foil, like a baked potato. And this is to achieve ultra high vacuum. Because normally, when we pump a system, it will be limited to about 10 to the minus 8 torr. And that is because there are always some molecules, especially water molecules, which will be absorbed in surfaces, and then they will dissolve. And so the pumping is and absorb again. And then so the pumping is not very efficient for at such a high vacuum. And so we had to bake out the whole stainless steel system to about 200 degrees to drive out the water vapor, and then they can be pumped away. So that's the reason for the aluminum foil. Now, here I also want to mention about here we have an electron gun, which is almost parallel to the substrate surface here. And then here we have a fluorescent screen. Okay, so the electron is a glancing incidence about 1.5 to 2 degrees from the surface, so that it monitors the surface condition. Okay. And this slide shows that when we polish a gallium arsenide surface with a bromine methanol, and then we heat it in vacuum to 580 degrees, and then so now supposedly oxide is already dissolved, and the surface is clean. Okay, so the sample is then cooled down, taken out, and then have a replica of the surface. And then we look at the SCM here. But on the left is the electron diffraction. Okay. And here we see that the surface is kind of rough. And so we see a three-dimensional electron diffraction. Then in the middle two slides is after growth, so 15 nanometer of gallium arsenide. And you see the surface becomes smoother, and the electron diffraction starts to be streaky pattern, meaning that we are going from 3D to 2D diffraction. And then after 1 micron of growth of gallium arsenide, you see the surface is very flat. And then here we see a two-dimensional electron diffraction. This diffraction is streaky because the third dimension is not defined. Okay. And so we use this electron diffraction to monitor the surface. First, the oxide layer is removed, because any time we put a material in air, we expose to air. So we have a thin layer, about 15 angstroms of oxide. Okay, so we have to dissolve it to expose the underlying single crystalline structure. And you see, so after we grow this, let's say 1 micron of gallium arsenide, the surface is atomically smooth. And so the electron diffraction, if we look at the specular beam, it's at the highest, okay, because the surface is smooth. Then as we deposit more, the first quarter of a monolayer, 0.25 here. And so these monolayer high islands, they form randomly on the surface. And so surface is rough. The electron intensity decreases, and there is more diffuse scattering. And then the surface is the roughest when we have a half monolayer. Okay. So there is a lot of diffuse scattering. The specular reflection is at the bottom. And then as we grow more, deposit more material, these monolayer high islands coalesce. And so the surface becomes smoother again. And the intensity increases. And then when we reach 1 monolayer, then the surface is smooth again. And then the intensity is the highest. So 1 cycle corresponds to the time to grow 1 monolayer of material, 1 atomic layer, which is 3.5 angstroms. Okay. And of course, initially, so after 1 monolayer, actually some region will be 2 monolayers, some region is 0. So statistically, it's going to be, so there's going to be some roughening of the surface. So the intensity actually will decrease somewhat. And in the growth of gallium arsenide, the gallium sticking coefficient is 1, meaning that one gallium atom is on the surface, then it sticks to the surface. Arsenic has a higher vapor pressure. Arsenic sticking coefficient is 1 if there is a free gallium. But if there is no free gallium, then the sticking coefficient is like 10 to the minus 5 or something like that. So our growth of gallium arsenide is controlled by the group 3 flux. Okay. And we can also have, so here we grow gallium phosphide. So we have gallium and we have thermally cracked phosphine into P2. And so when we open the gallium shutter, then we see this oscillation determined by gallium. And then we stop gallium, stop the phosphorus, close the phosphorus shutter. We deposit gallium, the surface becomes rough. Okay, so after maybe 10 monolayers of gallium, we open the phosphorus and we see this oscillation again, meaning that we have excess gallium amount on the surface. And so that the surface is hot, so atoms moving around, and then now we have phosphorus coming in. Then we form monolayer high islands. Again, we grow this gallium phosphide layer by layer. And so here we can plot growth rate as a function of 1 over the gallium cell temperature. Or here, because I have gallium phosphide, aluminum phosphide, indium phosphide. So 1 over the group 3 cell temperature. As you can see, if I increase the cell temperature, the flux is higher, growth rate increases, and 1 over T decreases. And so this growth rate increases until, if I look at this example, until now the growth rate is limited by the amount of phosphorus. And so the growth rate flattens. And so this kink here determines the 5-to-3 incorporation ratio, very precisely. And we want to grow at the 5-to-3 ratio slightly greater than 1, because if it's less than 1, then we have excess amount of group 3 atoms on the surface, and the surface becomes rough. Okay. So this is the condition we want. So that's how we determine our growth. Now, the motivation for growing dilute nitride started more than 20 years ago. And at that time, if we look at this band gap as a function of lattice constant, we see gallium nitride here, a very large band gap, small lattice constant. Gallium arsenide is here, okay? So that, and indium phosphide is here. So the the reason for looking into nitride or mixed arsenide nitride is that if I incorporate nitrogen, say 20% nitrogen into gallium arsenide, I'm going to have a direct bandgap material which is lattice matched to silicon. Okay, so that's kind of attractive. And so actually we started this work in 1996. And what we found is that instead of this bandgap increases with increasing nitrogen concentration, as we just draw a linear interpolation, instead the bandgap actually decreases, and decreases quite rapidly. And so it's a huge bandgap bowing like this. And to explain a band anti-crossing model proposed. So here I plot the energy, conduction band energy, functional wave vector. And so this red line is the conduction band of gallium, okay? And in the middle here is zero momentum or zero wave vector. Horizontal line is a nitrogen energy level in the dilute limit. Because of the Heisenberg uncertainty principle, right? If nitrogen is isolated, we know its position well. And so its momentum is, we don't know, cannot be determined. And so that's why it's a horizontal line like this. But you see here, the nitrogen and the level and the gallium arsenide conduction band, they cross. But in physics, they do not want to be crossed. Okay, so there is this band anti-crossing. So we have a lower conduction band and the E minus and the higher conduction band. So this is like two hydrogen atoms forming a hydrogen molecule, right? We have 1s energy levels. When the hydrogen atoms are brought close together, anti-crossing happens, right? One becomes a bonding orbital and anti-bonding orbital. So this is the same situation. And so that's why the bandgap decreases because of the lowering of the conduction band. Okay. And this has a lot of ramifications. So the first is we apply to bipolar transistors. So here I show a band diagram of a bipolar transistor. We have a N-type emitter here, P-type and N-type collector, right? So we apply 4 bias in the emitter and base so that we use emitter-base barrier. Electrons are injected from emitter to the base. The base is thin, so the electrons are collected to the collector. But while the electrons in the base is positive, is negatively charged. So in order to keep charge neutrality in the base, positive charge is induced. Okay, so that's why. And we have more positive charge, and so we have more electron goes through. And so that's why you have gain, right? You have collector, a lot of electrons in the collector, divided by a small number of holes in the base. Okay. Now, so this is the principle of bipolar junction transistor. Now, but to lower the power dissipation, to lower the base band gap, because if you look at the collector current here, the collector current is affected by two exponentials. One is in this Ni squared. So Ni is an intrinsic carrier concentration. And this Ni exponentially depends on the band gap, right? The smaller the band gap, intrinsic carrier higher, exponentially higher. So this exponential function. The other exponential function is the base emitter bias. So here, so we have these two exponentials. And so in order to reduce for the same collector current, in order to reduce the base emitter bias, we should reduce the band gap. Okay, so we put the nitrogen into gallium indium arsenide base, and so the band gap is reduced. And well, of course, the problem here is that we have large conduction band offset, which acts as an electron barrier. So we have to provide some grading to eliminate this barrier. But I'll not talk about it here. But here is a result. We see the collector current, and this gray line is for gallium arsenide HBT. Gallium arsenide, indium gallium arsenide HBT. And then we put nitrogen into the base, and you see that we reduce the base emitter voltage, and but reduced to here, reduced by like 40 by 0.4 volts. And this is actually we also here we grade the base to improve the electron transport, but that's beside the point. But this actually was put into manufacturing. So Kopin Corporation, in fact, they advertise their GaN HBT. So GaN here is gallium arsenide, indium nitride, HBT. So here we have this GaN. Okay, so that's their commercial product. Now the other application is with this band gap reduction is in solar cells. Here I show the solar spectrum, okay, and then here is a function of wavelength, and here I have a silicon solar cell, and 1100 nanometers, so that's about silicon band gap. And you see the conversion efficiency is high here near the band gap, but decreases when the wavelength is shorter. And this is because of the heat loss. You see, because here, the photon energy is just above the band gap energy, I create electron hole pairs. Okay? And then because of the PN junction, electron and holes are separated. Now, if the photon energy is higher, and I create electron hole pairs like this, so electrons and holes, they want to lose the energy very quickly to the bottom of the conduction band or the top of the valence band, and then they get separated. And so this energy is lost as heat. Okay, so that's why the conversion efficiency decreases. And to improve this efficiency, people use multi-junction solar cells. So here we have 3 junctions. Okay, the top has a larger band gap. So the photon, high energy photon is absorbed. Middle and low energy photon is passed through and then gets absorbed in the middle, and then later absorbed. The low energy photons absorbed at the bottom. So you can see that I have strong efficiency here, and then I start to decrease the conversion efficiency. But I have a middle band gap. Okay, so it increases again, and then lower and increase again. So you can see this conversion efficiency for multi-junction solar cells should be much higher than just a single junction solar cell. Okay, and this shows the solar spectrum again, and the AM 1.5D is still kind of the average solar spectrum in the AM0 is without the atmosphere absorption. AM1 is on the Earth's surface, but because that's for perpendicular sunlight onto your solar cell, but because of the sun moving and so we average 1.5. So here we have 3 junctions. Okay, or ideally we can have 4 junctions here, like where germanium, which is lattice-matched to gallium arsenide, a new material, 1.0 eV material, gallium arsenide 1.4 eV, and gallium indium phosphide 1.8 eV. So this 1 eV would be gallium indium nitride arsenide, dilute nitride, would just fit the bill. And this was at the time in this year, 2012, 2013, has this National Renewable Energy Laboratory measures solar multi-junction solar material by company Solar Junction, and so it has the highest efficiency, world record efficiency at the time. Okay. So now I want to talk about the effect of this lowering of the conduction band, because it's going to result in a larger delta EC conduction band offset, which means that it should have a better high temperature performance if our quantum well is made of dilute nitride. Okay, so here I show the energy as a function of strain. On the left, compressive strain. I put indium into gallium arsenide, so the lattice constant is larger, and so it's relative to gallium arsenide. It's a compressive strain. But on the other hand, nitrogen atom is smaller, so we have a tensile strain. So if in the beginning I have, say, point A, I have this so much compressive strain, gallium indium arsenide, I incorporate nitrogen, I actually reduce the strain. Okay, so that's one big positive point. The other is this increased delta EC. So increased delta EC, as you can see, at some high temperature, this electron in this quantum well may gain enough thermal energy and escape. But if the barrier is larger, it cannot escape. Okay, so it should have a better high temperature performance. And so here's an example that we have indium phosphide, we have indium gallium arsenide phosphide, and then we incorporate nitrogen, indium nitrogen arsenide. Okay. And then here is a barrier again. And this is in collaboration with Professor Sengtian Ho of Northeastern University. So then he made into a micro disk. Okay. So, and lasing in this micro disk is called a whispering gallery mode, because the electron circulate along the edge. If I put a notch here, I have light coming out tangential. And here I show how with incorporation of nitrogen, delta EC is increased. Okay. And as a result, we have a higher temperature operation. So this is a indium gallium arsenide phosphide quantum well, and we compare with dilute nitride quantum well. And you see the indium gallium arsenide phosphide, indium gallium arsenide quantum well saturate. Okay. But here, there is no saturation. And the operating temperature for this one is 220 degrees Kelvin. And for this one is 330 degrees Kelvin. And this shows the threshold power. This incident excitation power is vertically, it's optical pumping. And threshold power goes like exponential T over T0. So the larger the T0, the smaller effect of the temperature. And so here, dilute nitride, we have a higher T0. So all these mean that we have a larger conduction band offset. Okay. So then the third effect is this band structure. So here I show gallium photoluminescence of gallium phosphide. Okay, with nitrogen, very small amount of nitrogen. So it's the dome range, like 10 to the 18 or something, and we see discrete nitrogen peaks. Okay. But incorporate more and more nitrogen, we actually see these there's a shift to longer wavelengths, and these discrete peaks coalesce into a band, and the band intensity actually increases. Okay. So this kind of indicates that well, we know first gallium phosphide is an indirect band gap like silicon, so it does not emit light. Okay. But the fact that we incorporate so much, just small amount of nitrogen, like 0.4%, or here 0.8%, that we form a band, okay, and high intensity. So kind of indicates that it's a direct band gap. It's just such a small amount of nitrogen incorporation. And indeed, if we collaborate, we send the samples to Professor Villanova at Linköping University. So okay, first here I show the difference between the direct and indirect band gap. You see here, once again, it's the energy as a function of momentum or wave vector. Indirect band gap, like silicon, minimal conduction band is some vector away, momentum away from the minimum of the valence band, or maximum of the valence band. And for gallium arsenide, it's a direct band gap. So direct band gap material emit light. What she found is that she looked at the photoluminescence as a function of time. You know, you apply a light, okay, then you create electron hole pairs, and then they recombine. Then you observe photoluminescence. And then as a function of time, you see how these light decreases. What you find is that for 0.24% nitrogen, the lifetime is long. But when it's 0.6% nitrogen, the lifetime is short. So if you plot lifetime as a function of nitrogen content, you find that at about 0.5% or 0.4%, there is the two groups, the long lifetime and the short lifetime. Now, short lifetime corresponds to direct bandgap because light emission is efficient. Okay, so the lifetime is short. But for indirect bandgap, electron is here, hole is here. In order for electron and hole to recombine to produce a photon, electron has to scatter with a phonon, with a lattice vibration, to go from, to lose its momentum to here, and then come down, and then recombine. And so this actually is a demarcation of direct bandgap and indirect bandgap theory. And so here, just very quickly, I show the because our emission light is like in the yellow or red. So this is how red LED, high brightness red LED produced. On gallium arsenide substrate, you grow a active layer, which is indium aluminum gallium phosphide. But gallium nitride is absorbing. Okay. And so we can either remove the substrate, grow a thick gallium phosphide layer, so to collect the side band, okay, the light emitting on the side. Okay. Or we remove the substrate, wafer bound to a metal carrier. Okay, so here's the metal, and so you get a reflection, and you extract more light. Or here you wafer bond first, and then remove the substrate. So here we shape the substrate, and so that we extract more light. So light extraction is important, but you can see all this involving substrate removal because the gallium arsenide absorbs this red light, short wavelength light. Okay. And so, but now we have a gallium nitrogen in gallium phosphide. Gallium phosphide indirect bandgap, and it's a large bandgap, it's transparent. Okay. And so we can make this into a one-step epitaxy onto a transparent gallium phosphide substrate. So in principle, we can eliminate the wafer bonding process. And so it should be cheaper. And so here we have gallium nitride phosphide compared to the regular LED. We have 3 times better electron confinement, so better high temperature performance, and we can operate higher current. And so actually, my student and I, we formed a company to do this. And so this is done by the company. So we compare light output as a function of temperature. And you see the higher temperature, this dilute nitride LED will have a larger light output. Okay. And so so that's about LED, how it improves the LED. Now I want to talk about the last application is solar cells. So here I show So gallium phosphide can be a wide bandgap solar cell because it has a proper energy, but so but because indirect bandgap, lower light absorption, so we need a much thicker layer, and the highest efficiency is like 2.9%, okay, with this aluminum gallium phosphide in window layer and anti-reflection coating. So here one is just a gallium phosphide. The other one is we have a dilute nitride, and then we have dilute nitride, thicker dilute nitride. So we compare these three samples. Here is 800 nanometer, 800 nanometer, and 2000 nanometer. And here shows the IV curves. So you can see this dilute nitride has a higher efficiency. Okay. Higher efficiency. Yeah, higher efficiency here. Okay, has a so this is a larger short circuit current. Okay. Small change in the open circuit voltage, and then this is a field factor. Okay, and then here is the efficiency, and this the larger number here is with anti-reflection coating. And so if we compare this dilute nitride with a gallium phosphide, we see that the external quantum efficiency is much larger. So it just shows that we have a direct bandgap material, we have better absorption efficiency, and then we need only 1/4 the thickness. Now, finally, so in recently, IEEE, a epitaxy and a device company, announced its IQDM VCSEL technology. VCSEL stands for vertical cavity surface emitting laser. And this is so VCSEL comes into, has a renewed interest because Apple introduced iPhone X in 2017 and it incorporates VCSEL. I have an iPhone 10 here. And you see that iPhone 10 over here, there are a few VCSELs. And currently the VCSEL is grown by MOCVD because it is. And here I explain the VCSEL, okay. You have, instead of regular laser is edge emitting, right? You have a wafer here and you clip the light coming out of the edge. But here with the VCSEL, vertical cavity has the advantages of lower beam divergence, it can be circular beam instead of elliptical. And then has a longitudinal single mode because the cavity is very short and no mirror cleaving, because we rely on the bottom and the top mirror. And these mirror were grown epitaxially, so by a gallium arsenide, aluminum arsenide, so-called distributed Bragg reflector. Okay. And so here's a VCSEL. And so here shows a Samsung smartphone, and we have a VCSEL here. Okay. And then here's a photo detector. So these are VCSEL are used for facial recognition. And okay. And so, but there's a renewed interest in long wavelength VCSEL because of two issues. One is I show you the iPhone 10. It has this notch here. Here we put several VCSELs and detectors. why don't you put here? Because this 940 or 980 nanometer light is absorbed by the glass, okay, by the display. And so so the goal here is 1380. The other issue is eye safety, because here I plot the maximum permissible exposure as a function of wavelength. And so here is like 980. Okay, here is 1310. Here is 1550. You can see this is for different pulse width of the light. So you can see that 1550 has a much higher, about 500 times the maximum permissible exposure as compared to 1310. Okay. So of course you want to do that. But to go to 1550, the problem is that it's not very practical, because you have to grow on indium phosphide substrate. Okay. Unfortunately, the indium phosphide-based material, the refractive index difference is not too different, 3.44 versus 3.2. Whereas the gallium arsenide, aluminum arsenide, 3.4 versus 2.9. So on indium phosphide substrate, you have to grow a much thicker layer. You have to have many more pairs to achieve the same reflectivity. Okay. And so the interest is to have these long wavelength emission on gallium arsenide substrate, so that we can utilize the commercially mature DBR technology on gallium arsenide. Okay. And so this is where the dilute nitride comes in. Okay, the larger delta AC, and we introduce antimony as a surfactant, because antimony is much larger, so it tends to float on the surface. Okay. So and flatten the surface. And again, here the larger delta EC. So now I mentioned all these advantages of dilute nitride, but there were attempts to commercialize it, but they're all failed. Until now, recently, we have renewed interest in VCSEL cell phone. And so the challenge is this: because we want to put nitrogen into the arsenic sublattice, but gallium nitride bond is much shorter, as you saw in the gallium nitride the lattice contact, much shorter than gallium arsenide. And so when we put a lot of nitrogen in, you get broken bonds. Okay, because the strength is too large. And so once you have broken bonds, these are dangling bonds, then they are, they can capture electrons, and so they reduce the light emission. Okay, and so the answer is try to use antimony, but still, it can increase the triple layer thickness from 2D to 3D, but still it's a challenge. And so to summarize, I talk about this. The reason for bandgap reduction in incorporating nitrogen can be explained by this band anti-crossing model, and then we have advantages due to lower bandgap, or larger conduction band offset, and change of band structure from indirect to direct. And so all this, has advantages. But I also mentioned about the challenge of this point defects, dangling bonds. But now there is a renewed interest in this long wavelength VCSEL for facial recognition and 3D sensing. Okay, thank you. So
thank you very much, Professor Charles, for enlightening.
You are muted.
Am I audible to you now?
I stopped share.
Yeah, are you able to hear me?
Professor Saxena, you are muted.
No, I've unmuted myself. Can you hear me?
I cannot hear you, unfortunately.
You're not able to hear me out.
Huh?
Okay, let me just ask the attendees. Am I audible to the attendees? Professor Charles, the attendees, they are able to hear me out.
Oh, somehow I cannot.
Okay, no problem. So what I'll do is I'll just
So
share.
something wrong with my.
Okay, no problem, no problem. So I'll just share my screen and let me share the questions which have been shared by the attendees.
Okay. Okay, first question is about gallium nitride, aluminum gallium nitride. But I will say, these are in completely different applications because gallium nitride, aluminum gallium nitride now is used for, of course, blue LED and white LEDs, and also high power electronic device. But here I'm talking about the gallium arsenide. We are talking mainly about optoelectronic applications. And for high power application, you have to go to gallium nitride system. Gradient polarization. Yes, yeah. About the second question, as long as you increase the delta EC, and if you use this material as a quantum well, then it should be the same. Larger the delta EC, you have a higher temperature operation. And so, yeah, it will be for efficient optical application. Trade-off between achieving higher band offset, higher mole fraction versus compound. Yes, yeah. So this is what I was talking about. Is a challenge of this dilute nitride, because we want a larger, more nitrogen, so that we have, smaller band gap, larger band offset, but then we have more defects. Okay, because of this downlink bonds issue, short gallium nitride downlink bonds, and localized heating, and the confinement well effect. Is it possible to employ material better thermal conductivity? Well, of course, we can have materials better thermal conductivity, but we are limited by the substrate. Okay, gallium arsenide is what we have, and it's the most common. Now we can produce 6-inch gallium arsenide. And so that we are limited by that. And so our architectural structures, all the device structures are grown on these on the gallium arsenide substrate. So we are kind of limited. MBE, a physical as well chemical. Well, MBE is a physical process. Okay, because it's a physical process in the sense that it's a line of sight deposition. And if you want to say, chemical process in the sense that, okay, we have a gallium and arsenic combined. So that's a chemical process. Is it verified through XRD, the film deposition over? Yes, yeah. So we can monitor our crystallinity by electron diffraction in situ, inside the machine. We have electron beam, and then we look at the diffraction pattern. So we can do it by in situ by electron diffraction, and we can take the sample out. We look at X-ray diffraction, and we should see these X-ray peaks, but also Hunter-Lawson fringes. All this interference due to these multiple layers. So, okay, so these are 5. Yeah, but I guess
Yeah,
they are,
I'll just check the chat section. No, I think that's all. That's all. Are you able to hear me
okay.
now?
Yes, I can hear because
Okay,
I
fine.
somehow I muted my
Okay.
I muted my speaker. I didn't
Okay.
touch it, but it got muted. Yeah.
Okay. Well,
Yeah.
thank you very much, Professor
Okay, I'm
Charles.
glad that it's all within time. Yeah.
Yes. And for sparing your valuable time and sharing all your experience and research activities going at your research lab with all the attendees over here. I would like to thank all the attendees also who have been there with us for the last 1 hour, and hope to see you all again in the next interesting session, which is scheduled for April 27th. And you'll get a Zoom invite a day prior to that session itself. Thank you very much, Professor Charles.
Okay. Thank you very much.
Thank you.
Thank you.
Right.
Yeah.
Bye-bye.
Bye.